if you take cones that look like this and you slice them all the different ways you can slice them, you wind up getting the shapes that we call conics. Parabola, circle, ellipse, and hyperbola. You've dealt with some of them before, but if you actually think about what the definitions of them are, everything else will fall into place, or at least can fall into place. For example, looking at the definition of parabola. The definition is the set of all points P in a plane for which P's distance to a fixed point is equal to its distance to a fixed line. So if we're looking at this parabola, we've got some fixed point over here and some fixed line over here. And I want to give these names. This is the focus. So let's call the coordinates of this fx and fy, the x and y coordinates of the focus. This line right here has some y value, y equals, let's just say d, because they call this the directrix. And this point, which is the vertex, is h comma k. And any point anywhere along here, any point at all, is just generically x comma y. And the definition says that this distance from here to here has to be equal to this distance from here to here. That's what makes this a parabola. Well, this distance is going to be the square root of x minus fx squared plus y minus fy squared. Okay? That's this distance right here, from here to here. From here to here, this distance is the absolute value of d minus y, because this is a vertical line, so I don't have to worry about the x stuff. So let's look at what we can do with that now. If I square both sides of this, if I set these two distances equal to each other and then square them to get rid of the radical sign, this is what this equation looks like. And if I actually do out all the arithmetic and then bring this part over to this side here, over here I just get x minus fx squared. But here I get d squared minus 2dy plus y squared, that's this thing squared, minus, since I'm bringing this over here, this thing squared. So it winds up being minus y squared plus 2y fy minus fy squared. If we simplify this, I put the y's together, I put the constants together, and I wound up with this, which is okay. And then I looked at this and I said, you know, I could factor something out here. And I did. I factored out the 2y and got 2y fy minus d. And then this I factored too, because this is the difference in squares. So I can turn this into the product of the sum and difference of the square roots. Then I looked at this, and I looked at this, and I thought, if I multiplied this by -1, it would be the same as this, and I could factor that out too. But then if I made this minus and multiplied this by -1, that would turn out to be the same. That's the same thing. So that's what I did. I made this a minus and flipped these two around. And I did that so that I could factor out this and be left with this. I don't really want the 2 in there. I'd like to have y by itself, because that's usually how we do these forms. So I factored out a 2. And I was left with 2 fy minus d y times y minus d plus fy over 2. Wait a minute, what is d plus fy over 2? Let's go back to the picture for a minute. Here's d, right? Here's fy. If I add them together and divide by 2, I'm going to get the y coordinate for the vertex, right? Well, that's pretty cool. So when I come back to this, right, this right here, this is going to be y minus k, right here, because that's what this is. Now let's look at this for a minute. Fy minus d. Fy minus d. Well, that's actually this distance here, isn't it? And if I'm talking about from the focus to the directrix, that's actually 2 times the distance from the focus to the vertex. Well, let's call that p. So then this minus this is actually 2p, and we've got this multiplied by 2 already. So 2 times 2p. So this is equal to 2p, and when I rewrite the whole thing, this is equal to k. When I rewrite the whole thing, oh, and by the way, fx, the x coordinate of this, it's going to be the same as the x coordinate of this. So it's going to be h. Okay. So if I just rewrite it, this is what I get. I didn't mess with this side. I left this side alone. This reduced all the way to this. This turned out to be k. This turned out to be 2 times the distance from the focus to the vertex. You guys had been asking me, where'd the 4p come from? Well, it just sort of sprang into being right there as a result of the definitions of all of this. And now, this is the form, and it tells you everything you need to know about parabolas. Right? From this, you know where the vertex is, you know the distance to the focus, which means you know the distance to the directrix. You can work all that out. This comes straight out of the definition. It's not something that you just memorized because somebody told you to. This comes from the definition. And they all do. The definition of a circle is the set of all points P on a plane such that for every point P, it has the same distance from a fixed point on the plane. So if this is the center of the circle, and this is x comma y, this distance from here to here is a constant r. And if we call this h comma k, in other words, it doesn't have to be at the origin, it could be anywhere, then x minus h squared plus y minus k squared, the square root of this has to equal r. If I square both sides, I get x minus h squared plus y minus k squared is equal to r squared. Again, it just comes straight out of the definition of a circle. Okay, so now let's mess with this a little bit. We could decide to divide both sides by r squared. If I do that, I've got r squared over here, r squared over here, and a 1 here. But now, what if I put different numbers in? Right? We'll call this RA and RB. Well, RA is going to be the radius from here to here. This one is going to be the distance from here to here. If they're different numbers, well, then the shape is going to be different. It's going to look more like this. The definition of an ellipse is all of the points P on a plane such that the sum of the distances of each point from 2 other points is always the same. We did this, if you'll recall, right? I taped up a piece of ribbon on the board and then used a pen to go around like this and show that if I kept the sum of the distances constant, the ellipse is what I wound up with. Take a look for a minute. If I go from here all the way to here and then back to here, if that was in order to get this vertex right here, the distance of the ribbon is actually, right, this distance right here is the same as this distance right here. So the sum of the two distances is actually equal to 2a. If this is a and this is a, then, and d1 is the distance from one point and d2 is the distance from the other point, adding them together gave me 2a. Wait a minute. What if I'm trying to get the distance from here to here, right? In order to get this point right here, that's an isosceles triangle. This is going to be equal to this, right? Which means, well, if this is half of the sum of the distance and this is half of the sum of the distance and the sum of the distance is 2a, that means this is a. This distance from this focal point to this covertex is the same as the distance from the center out to this vertex. This is B. And frankly, this distance right here, from here to here, well, it's a right triangle. Pythagorean theorem says this squared plus this squared equals this squared. So if I'm writing this in terms of these two, this is going to be the square root of this squared minus this squared. That's the distance from here to here. And I already have a squared and b squared. They're part of my equation. So the distance from here to here is the square root of 5. Okay? Which then means, oh look, if I know the center from the equation and I know the a and the b from the equation, I can get these points fairly easily. And of course, if I know these points, then I can work backwards to get the equation. So then what happens if we just mess with the equation and instead make it minus? Okay. So you'll notice that what I did here, I changed it so that a is 5 and b is 4. Right? So this is what would happen if I just took the equation for the ellipse and made it minus instead of plus. This is what would happen to the ellipse if I made the first one minus and the second one plus. So now I'm looking at this, I'm thinking, well, which one of these goes to which one of these? Well, here's a way to think about it. Right here, this is where x is equal to 0, right? Let's plug x equals 0 in here. I get 0 over 25 minus y squared over 16 is equal to 1. Well, this is 0. If I multiply both sides by 16, I have minus y squared equals 16. Is there an answer to that? Not in the real system, right? Not in the real number system. So that means on a real coordinate plane, real number coordinate plane, this equation right here cannot cross the y-axis. So that's this one right here. This one and this one. The same thing goes this way, right? If I put in, this time 0 for y, if I put in 0 for y, I get negative x squared is equal to 25, and that's not going to have a solution. So this one, if the x is negative, it's got to open this way. If the y is negative, it has to open this way. And now, there are asymptotes here. This thing gets closer and closer and closer to this line as it goes out to infinity, and closer to this line as it goes out to infinity. And these two lines cross in the center of what this whole thing is. And essentially, I could draw a little rectangle here. And if you look carefully, you'll notice that this distance from here to here is A, and this distance from here to here is B. And this actually cuts through the corner of this rectangle, and this one cuts through the other corner of the rectangle, which actually means we know the slope of these two lines. This is plus and this is minus B over A. And if HK is the center, this line is going to go through the center. And if I know the slope and the and a point on the line, I can write what they call the point slope form of the equation, which is y minus y1, which in this case would be k, is equal to b over a plus or minus b over a, because that's my slope, times x minus h, which coincidentally are these numbers right here. So in order to get the equation for the asymptotes, I just take these numbers right here and do this with them. Now, I know that the book and all of the papers we've looked at, when this is positive and this is negative, they switch them, and then they switch the A and the B, and then it goes the other way. But the truth is, the equations for these two lines are going to be the same whether this is positive or negative. So the only difference the positive or negative makes is which way it opens. And that you can figure out by looking at the zero value for x and the zero value for y. Yeah.